Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the superposition theorem as applied to DC circuits. Our objective today is to learn to employ the superposition theorem in an effort to solve for desired electrical quantities for circuits with more than one source. Bottom line up front, the effects add up. The superposition theorem is the simplest and most reliable of circuit analysis techniques because it makes so much intuitive sense. When tasked with carrying a couch upstairs with a group of your rowdy friends, it helps when they're all pushing in the same direction. If one of your stupider friends is under the assumption you're moving out rather than moving in, their opposition reduces the resultant effects. If you are the stupid friend opposing everyone's combined effort, your contribution will be overwhelmed. Long story short, don't have stupid friends help you move a couch upstairs. Ask me how I know. As applied to electrical circuits, the superposition theorem is simply series parallel circuit analysis of the same circuit with multiple sources from the perspective of each individual source, and then the individual results are summated, accounting for magnitude, polarity, and direction. This implies one must be skilled in series parallel circuit analysis to apply the superposition theorem, and this lecture operates under the presumption you have mastered the contents of the DC Series Parallel Circuit Analysis lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. In addition to reliable series parallel circuit analysis skills, one must also have a modicum of organizational ability to properly apply the superposition theorem. Regarding polarity and direction, one must be able to differentiate between left, right, up, and down. I'm your electronics instructor, not your mama. I cannot teach you to be organized. Your mama should have taught you to put things where they belong and the difference between right and left, up and down, and good and bad. The only judgment I'm making about you is whether you're right or wrong. Stay organized and remember to account for direction and polarity. When source 1 pushes 1 amp of current through a 10 ohm resistor, left to right, and source 2 pushes 1.5 amps of current through the same resistor, right to left, and source 3 pushes 0.75 amps or 750 milliamperes of current through the same resistor, left to right, the summation of these three currents is 0.25 amps or 250 milliamperes going left to right, and it is not 3.25 amps. If you cannot understand and differentiate between the utter rightness and sheer wrongness of these two diametrically opposed results, send me your mama's phone number because I'm going to call her up and have her slap you silly for being messy and unorganized. This housekeeping trick also works for voltage polarity. Given the above-mentioned current directions, source 1 would induce a 10-volt drop across this resistor, positive to negative, left to right. Source 2 would induce a 15-volt drop across this resistor, positive to negative, right to left. And source 3 would induce a 7.5-volt drop across this resistor, positive to negative, left to right. Accounting for polarity, the summation of these individual voltage drops would mean this resistor would experience a 2.5-volt drop left to right. It is an act of sheer wrongness to suggest that this resistor would experience a 32.5-volt drop, accounting for polarity. A swat from your mama's firm but just hand will attest to this wrongness. Wrapping back to our earlier current analysis, it can be demonstrated that a 2.5-volt drop, positive to negative, left to right across a 10 ohm resistor, would induce 250 milliamperes of current traveling left to right. Conversely, a 10 ohm resistor experiencing 250 milliamperes of current traveling left to right would mean that there is a 2.5 volt drop across it, positive to negative, left to right. This is to suggest that results should be supportive of one another, and there exist ample opportunities to check your work via Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law. Before you run off under the mistaken assumption that the superposition theorem is the best thing since they replaced the turd brown M&M with a blue one, let me warn you that the superposition theorem has its disadvantages, tricky spots, and limits. The principal disadvantage of the superposition theorem is that it requires independent analysis of the same circuit from the perspective of each source. If your circuit has two sources, this means two independent analyses and a final summation. If your circuit has three sources, This means 3 independent analyses and a final summation. If your circuit has 100 sources, you may wish to investigate the use of a computer to solve for desired electrical properties. You get my point. Other circuit analysis techniques like mesh and nodal analysis can yield the same results in a single, admittedly convoluted step. However, these techniques necessitate special math skills with little carryover value outside these limited circumstances. This being said, the reason I'm such a big fan of superposition is that it yields reliable results using skills you should already feel comfortable with applying, notably traditional series parallel circuit analysis. Why learn special skills when the skills you already have yield the same results? The back of an axe makes an excellent substitute for a hammer, in addition to the ability to chop things to pieces. Granted, you may not want to build fine cabinetry with an axe. However, in a pressing survival situation, you can quickly turn fine cabinetry into firewood with the axe. Additionally, the superposition theorem does come with some attached trickery. As we'll later learn when we dive into the illustrated example problems, the superposition theorem necessitates a removal of sources not currently under consideration with the incorporation of shorts and opens. The addition of shorts and opens may fundamentally change the nature of the as-analyzed circuit. Recall that opens present an infinite resistance through which no current will flow. Shorts present no resistance, which all current will flow in preference to all other paths. We'll discuss these modifications in greater detail when we apply the superposition theorem to the illustrated example problems. Finally, the principal limit of the superposition theorem is that of linearity, in that only linear sources and linear properties can be summated using the superposition theorem. This is to suggest that Ohm's law for linear sources is cool, whereas power is not cool. Power, being the product of voltage and current, is not a linear property, but rather geometric in nature. The power dissipated by a component from the perspective of individual sources is essentially nonsense, and power effects are not additive. This being said, the final summated voltage and current, where polarity and direction have been properly accounted for, can then be used to solve for final power. Again, considering our earlier example of the 10 ohm resistor being acted upon by 3 sources, the final voltage of 2.5 volts and the final current of 250 milliamperes can be used to determine that this resistor is ultimately dissipating 625 milliwatts of power, and not the summation of 10 watts, 22.5 watts, and 5.625 watts. Even if you assume source 2's contribution to be negative, this still yields an incorrect result. Either method is utter nonsense because power is a nonlinear property, and the superposition theorem only applies to linear sources and linear properties like Ohm's law. Here's the procedure I use to employ superposition theorem to solve for desired electrical properties. We'll go over each step in detail during the illustrated example problems. However, the 4 general steps are as follows. 1. Identify the source of interest. Remove all other sources from consideration. Current sources are removed by substituting an open circuit. Voltage sources are removed by substituting a short circuit. Be warned that substituting an open or short may fundamentally change the nature of the as-analyzed circuit. Redraw the circuit. Note that I've underlined this particular passage. To clarify, I am asking you to redraw the circuit. Step 2. Perform series parallel circuit analysis of the as-analyzed circuit for the desired electrical properties. Take note of not only the magnitude, but also the polarity and direction of desired electrical properties. Step 3 has us repeat steps 1 and 2 for all sources. This means our 4 general steps is in actuality a flowchart, and we need to repeat steps 1 and 2 as many times as there are sources in our circuit. Finally, when we've run out of sources, we can move on to step 4. Summate all linear properties, taking into account magnitude, polarity, and direction. Nonlinear properties like power can then be solved for at this time using the final voltage and current values. Consider this series parallel circuit with multiple sources. IA is a 40 milliampere current source, and EB is a 12 volt source. R1, R2, and R3 are all 500 ohm resistors in a delta configuration. Let's apply the superposition theorem to solve for the voltage drop across and the current through each resistive element. This is one of my favorite circuits to begin discussion of superposition theorem with, since it dramatically illustrates the effects of opens and shorts in the as-analyzed circuits. Let's start the analysis from the perspective of the IA current source. This means we need to remove the EB voltage source by replacing it with a short. Note that when we redraw the as-analyzed circuit, including the short, the nature of this circuit has fundamentally changed in that all current entering this node will travel through the 0 ohm short rather than the parallel path afforded by the 500 ohm R3 resistor. It can be stated that I3 is 0 amps, and since no current is flowing through R3 from the perspective of IA, there will be no voltage drop across it. This sets us up for a perfect current divider rule. However, given that R1 and R2 are both equal resistors in parallel with one another, it can be stated that 40 mA will divide evenly between them, where both resistor 1 and resistor 2 carry 20 mA of current each. Given the direction of current, the voltage drop across R1 and R2 will have the following polarities, and Ohm's law states that they will both have a 10-volt drop. Now we need to repeat this analysis from the perspective of the EB source. When analyzed from the perspective of the EB voltage source, we need to remove the IA current source by replacing it with an open. Note that when we redraw the as-analyzed circuit, including the open, the nature of this circuit has fundamentally changed in that no current can travel through the open, and all current will be confined to the following paths. Given R3 is perfectly in parallel with the EB source, we can say that there is a 12-volt drop across it, and Ohm's law dictates that there will be 24 mA of current through it, where the polarity of the voltage drop is positive to negative, top to bottom, and current will travel top to bottom. Given R1 and R2 represent a series path in parallel with EB, the voltage divider rule can be used to find that R1 experiences a 6-volt drop, as does V2, with the indicated polarities. Note that the voltage drop across R1 from the perspective of the EB source is in opposition to that of the IA source. Note that the voltage drop across R2 from the perspective of the EB source is aiding that experienced by the IA source. We'll return to these properties in a moment. Ohm's law dictates that 12 mA will travel through R1 and R2 with the indicated directions. Now that we've completed independent analysis of the circuit from the perspective of both sources, the only task remaining us is to summate the effects accounting for magnitude, polarity, and direction. The current through R1 as induced by the IA source is in opposition to that induced by the EB source. It can be stated therefore that 8 mA of current travels through R1 in this direction. The voltage drop across resistor 1 as induced by the IA source is in opposition to the voltage drop induced across resistor 1 as induced by the EB source. Therefore, the polarity of V1 is 4 volts southwest to northeast. Note we can check our work in the fact that 8 mA through a 500 ohm resistor would induce a 4-volt drop across it. Additionally, a 4-volt drop across a 500 ohm resistor would induce 8 mA of current to travel through it. Current through resistor 2 induced by both sources is additive in that both sources compel conventional current to travel northwest to southeast. I2 is therefore 32 mA. V2 will also have additive voltage polarity in that there will be a 16-volt drop northwest to southeast. Given that source IA induces no current through or voltage drop across R3, it can be stated that the values obtained from analysis of the EB source dictate R3's behavior, where 24 mA of current travels downwards and R3 experiences a 12-volt drop. Note that 40 mA of current enters this node and 8 plus 32 or 40 mA of current leaves it. Note that at this node 8 mA of current enters it and 24 mA of current leaves it via the R3 path, meaning EB is supplying 16 mA of current. At the bottom node, 32 plus 24 or 56 mA of current enters it, and 16 plus 40 or 56 mA of current leaves it. I've got a reasonable degree of confidence our answers are correct. Let's try another illustrated example problem. By all means, pause the lecture and see if you can apply the superposition theorem to solve for the voltage drop across and the current through each resistive element. In this case, IA is a current source of 100 milliamperes, EB is a voltage source of 10 volts, R1 is a 100 ohm resistor, R2 is a 400 ohm resistor, and R3 is a 200 ohm resistor. If you did everything correctly, you redrew the circuit as follows from the perspective of the IA current source. When removing EB by replacing with a short, all current entering this node will travel through the 0 ohm short rather than the path afforded by the series combination of R2 and R3. I2 and I3 are therefore 0 amps, and R2 and R3 will both experience 0 volts drop. From the perspective of the IA current source, this means R1 will experience 100 milliamperes of current left to right, and Ohm's law dictates it will experience a voltage drop of 10 volts, positive to negative, left to right. When analyzed from the perspective of EB source, we remove current source IA by replacing it with an open. No current can travel through the open, and all current will be confined to the following path. R1 will experience 0 amps of current and will experience a 0 volt drop. The voltage divider rule states that R2 will experience approximately 6.7 volt drop, positive to negative, left to right, and R3 will experience approximately 3.3 volt drop, positive to negative, top to bottom. In this case, both R2 and R3 will experience approximately 16.7 milliamperes of current. Now that we've completed independent analysis of this circuit from the perspective of both sources, the only task remaining us is to summate the effects accounting for magnitude, polarity, and direction. R1 experiences 100 milliamperes of current traveling through it left to right, and as such experiences a 10 volt drop across it left to right. Both R2 and R3 experience approximately 16.7 milliamperes of current traveling through them with the indicated direction, meaning at this node, the current source is backfeeding an approximately 83.3 milliamperes of current through source EB, such that at the bottom node, 100 milliamperes of current leaves it. R2 experiences a 6.7 volt drop in the following direction, and R3 experiences an approximately 3.3 volt drop with the indicated polarity. Let's try another illustrated example problem. By all means, pause the lecture and see if you can use the superposition theorem to solve for the voltage drop across and the current through each resistive element. Before you begin, here's a hint. The inclusion of shorts or opens may change the fundamental nature of the as-analyzed circuit. From the perspective of the EA voltage source, we'll remove source EB by replacing it with a short. This means that any current entering this node will travel through the path afforded by the 0 ohm short rather than the R2 or R3 resistor. I2 and I3 are therefore 0 amps, and V2 and V3 will both be 0 volts. R1 therefore experiences the 12 volt drop, positive to negative left to right, and R1 will experience 60 milliamperes of current traveling left to right. From the perspective of the EB source, when EA has been removed by a short circuit, the short circuit has fundamentally changed the nature of this circuit, in that R1, R2, and R3 are all placed perfectly in parallel with one another. Voltage across elements in parallel is the same. All resistors experience an 8 volt drop. Note, however, that the polarity of V1 is 8 volts positive to negative, right to left. V2 positive to negative is top to bottom, as is R3 positive to negative, top to bottom. Ohm's law dictates that 40 milliamperes of current will travel through R1, right to left. 20 milliamperes of current will travel through R2, top to bottom. And approximately 13.3 milliamperes of current will travel through R3, top to bottom. Now that we've completed independent analysis of this circuit from the perspective of both sources, the only task remaining us is to summate the effects accounting for magnitude, polarity, and direction. I1 as induced by EA is 60 milliamperes of current left to right. I1 as induced by EB is 40 milliamperes of current right to left. The summation of these two currents, as induced by the separate sources accounting for direction, means R1 will ultimately experience 20 milliamperes of current traveling left to right. Ohm's law and the summation of voltage drops induced by independent sources accounting for polarity both dictate that 4 volts will be dropped across R1, positive to negative, left to right. Since the electrical properties of R2 and R3 are dictated only by the EB source, we'd state that I2 is 20 milliamperes of current traveling downwards, and I3 is 13.3 milliamperes of current traveling downwards. And both V2 and V3 are 8 volts, positive to negative, top to bottom. A KVL analysis of this loop starting here and traveling in this direction yields a 12-volt rise, followed by a 4-volt drop and an 8-volt drop. What goes up does indeed come down. A KCL analysis of this node sees 20 milliamperes of current entering it and 20 plus 13.3 milliamperes of current leaving it. Therefore, source EB will be supplying approximately 13.3 milliamperes of current to this node. An alternate way of thinking about this is from the perspective of EB when EA has been removed from consideration. In this case, R1, R2, and R3 are placed perfectly in parallel with one another, where EB must apply the summation of I1, I2, and I3 for source current, where this source current is 40 plus 20 plus 13.3 milliamperes. However, when countered by the effects of EA, EB is now a short circuit, which forces 60 milliamperes of current in the opposite direction. Therefore, EB is relegated to only supplying 13.3 milliamperes of current to the top node. Okay, one more illustrated example problem will close up shop and call it a day, provided you get it right. By all means, pause the lecture and take a stab at this. I'm asking you to use the superposition theorem to solve for the voltage drop and the current through each resistive element. In this case, we've got 3 sources. EA is a 24-volt source, EB is a 12-volt source, and IC is a 30 milliampere current source. R1 is a 200 ohm resistor, R2 is a 400 ohm resistor, and R3 is a 500 ohm resistor. You're on your own. From the perspective of EA, EB is removed and replaced with a short, and IC is removed and replaced with an open. No current can travel through the open, and all current will be confined to the series path. R1 will experience 40 milliamperes of current traveling through it left to right. R2 will experience 40 milliamperes of current traveling through it top to bottom. R3 will experience no current. The voltage drop across resistor 1 will be 8 volts, positive to negative left to right. The voltage drop across resistor 2 will be 16 volts, positive to negative top to bottom. And R3 will experience no voltage drop. From the perspective of source EB, EA is replaced with a short circuit, and IC is replaced with an open circuit. No current can travel through the open, and all current will be confined to a series path. In this case, R1 will experience 20 milliamperes of current, right to left. R2 will experience 20 milliamperes of current, bottom to top, and R3 will experience no current. The voltage drop across resistor 1 is 4 volts, positive to negative, right to left. The voltage drop across resistor 2 will be 8 volts, positive to negative, bottom to top, and resistor 3 will experience no voltage drop. From the perspective of the IC current source, both EA and EB are replaced with short circuits, meaning current will be confined to the following paths. In this case, current source IC must force 30 milliamperes of current through R3 right to left. At the top node, one can use the current divider rule to find that 20 milliamperes of current travels through R1 right to left, and the remaining 10 milliamperes of current travels through R2 top to bottom. Given these current figures, Ohm's law can be used to solve for the voltage drop across each individual element, where R1 is determined to have a 4-volt drop, positive to negative, right to left. R2, from the perspective of the IC current source, is perfectly in parallel with R1. Voltage drop across elements in parallel is the same. V2 will be 4 volts, with a polarity positive to negative, top to bottom. R3 will have a 15-volt drop, positive to negative, right to left. Now that we've completed independent analysis of this circuit from all 3 sources, the only task remaining us is to summate the effects accounting for magnitude, polarity, and direction. Given R1 experiences an 8-volt drop left to right, a 4-volt drop right to left, and a 4-volt drop right to left, it effectively experiences a 0-volt drop, and no current will flow through it. R2 experiences 40 milliamperes plus 10 milliamperes going top to bottom, and 20 milliamperes going bottom to top. The combined effect is 30 milliamperes of current traveling downwards. Ohm's law dictates that there will be a 12-volt drop across it, positive to negative, top to bottom. This is supported by the summation of each individual source's contribution to the combined effects. R3 experiences a 15-volt drop, positive to negative, right to left, and 30 milliamperes of current traveling through it, right to left. The KVL analysis for this loop starting here and traveling in this direction yields a 12-volt rise produced by source EB, a 12-volt rise across R2 given our direction of travel, a 0-volt drop across R1, and finally a 24-volt fall across source EA, accounting for direction and polarity. 24-volt rise does in fact yield a 24-volt drop. What goes up does indeed come down. This goes to show you by balancing magnitudes of sources and individual components, we can effectively balance out the voltage across individual components such that there is no voltage drop nor any current through them, as in the case of R1. If there is no current through R1, no current is entering the top node from R1. Therefore, 30 milliamperes of current enters it and 30 milliamperes of current leaves it. Our results support this conclusion. I've got a reasonable degree of confidence our answers are correct. Alright, that's enough example problems for today. By this time, you should feel confident enough to apply the superposition theorem without any outside assistance. If you're still having issues, please take the time to revisit this lecture and correct any misconceptions you may have about this technique. Very often, it isn't necessarily the electrical concepts, but rather organizing the results of the independent analyses and accounting for polarity and direction that trips students up when employing superposition theorem for the first time. Current with the wrong direction or voltage with the wrong polarity can have disastrous consequences. Take your time when summating results. Don't trust your calculator and always treat results as suspect until verified by other means like Ohm's law, KCL, or KVL. In conclusion, we learned to employ the superposition theorem in an effort to solve for desired electrical quantities for circuits with more than one source. Special use techniques like mesh and nodal analysis can yield the same results. However, the superposition theorem does so using techniques you should already feel confident in, notably traditional series parallel circuit analysis. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.